Good evening, everyone.
Good evening, ma'am.
Okay, am I audible?
Yes, ma'am, you are audible.
Okay, okay, thank you. So, today we'll start with the first unit of analytical chemistry, the first class of PGDAC, that is the general perspective of analytical chemistry. So, today we will cover two sections. So, in the first unit, we will be talking about a brief introduction to analytical chemistry, like the general perspective, the different analytical methods, the importance of analytical chemistry, the various processes that are used in analytical chemistry, and how this analytical chemistry is useful in our day to day lives, and why this is particularly important for everyone, not only for chemistry students or chemists, but for everyone in general. So, before we begin, we'll have a brief introduction about what is analytical chemistry. Now, as the name suggests, analytical chemistry, it deals with the analysis of different types of materials that we come across. So, here in this section, we will be dealing with the various types of instruments, the various methods that we generally come across analytical chemistry. And this unit, the unit 1, this is particularly easy because in this unit we will just be talking about the various analytical methods, and gradually we will talk about the various principles and the uses the of analytical chemistry of various different and their instrumentations in the coming sections. So today start with what is analytical chemistry. Now, here, analytical chemistry, it is not only important in the field of chemistry, but it is very much important in the field, in everyday field, like starting from from environmental chemistry to materials chemistry, to even for also biological samples in the field of geology, computers, and biochemistry, and particularly such fields. So here, this analytical chemistry, it concerns with the practice of the actually this analytical chemistry, it concerns with two major aspects. One is the quantitative analysis and other is the qualitative analysis. So whenever we come across a material, we an unknown material, we first try to understand what is its qualitative nature, and then once we get a preliminary idea about its qualitative nature, then we get to know its quantitative nature. So both this qualitative analysis and quantitative analysis, they are very much important to determine the properties of materials. These materials, they can be like food materials, medicines, drugs, and which we and other such things that we come across day to day lives. So here, this analytical chemistry, this can be divided into three major groups. Like the methods that are used in analytical chemistry have been classified in terms of chemical methods, physical methods, and physiochemical methods. So the chemical methods, these are the classical methods, whereas the physical and the physicochemical methods, they are the actually they have been termed as the instrumental methods of analysis. So here in the physicochemical methods, we will be dealing with the various types of instruments that are detrimental in analytical chemistry. So we will be gradually going towards that. Now, one of the methods that has to be that needs to be called as an analytical technique, it needs to be based on the amount of the substance that is present inside our particular material. So that is what we call it as the quantitative. So whenever we come across the word that it is quantitative analysis, this means that we are dealing with the exact amount of the matter. But whenever we say that it is a qualitative analysis, so that implies that we are just talking about the nature of the material. It does not talk about the amount of the substance that is present in the material. So this is two fundamental aspects of analytical chemistry, that is quantitative and another is qualitative. Now we will talk about the various classification of different analytical techniques. So here we know analytical techniques, it is very crucial for chemical analysis, and these analytical techniques, they have been classified into certain groups. The first is the chemical methods of analysis. Here in this method, the analysis of the substance or the analysis of the material under examination is done through different chemical methods. Similarly, electrical methods of analysis, where the analysis is performed by considering the different electrical properties of the material. The third is the optical methods of analysis. The fourth is the nuclear radiation method of analysis. The fifth is the analysis that utilizes the thermal property, or that is called as the thermal methods of analysis. And the last part is called as the separation methods, like the various methods, separation methods that are used in analytical chemistry. Now, these methods, they have been further classified into different techniques that are dependent on the measurement of the characteristic property or the quantitative nature of the sample. So first here we will talk about the chemical methods of analysis of different substances. So to begin with, as the name suggests, the chemical methods here, in the method of by analysis of a material by chemical methods, these methods, they play a primary role. So first, the preliminary method, the preliminary analytical technique to be done here is actually carried out in two procedures. One is known as gravimetry and the other is known as volumetry. Gravimetry particularly, it concerns with the weight of the material, and volumetry, it concerns with the measuring the volume of the material. So these two, gravimetry and volumetry, since they were developed, like they are the first two methods that have been used for chemical analysis of a substance, and they were the first developed at early stage. So these methods are now called as chemical methods of analysis. But in today's world, we also perform this gravimetry and volumetry to have a preliminary idea or a basic idea about the nature of our material. Now, so what is gravimetry? Whenever we come across the word gravimetry, we must understand that it relates to the weight of the substance. Gravimetry is actually a macro analysis procedure, and it depends upon the type of the chemical reaction that the material has undergone. So whenever we come across a chemical reaction, we see a precipitate is formed. So this product or the precipitate, we dry it and then we weigh it. So this amount, after weighing our product, we can actually compare the amount of reactants that we have taken and the amount of product that we have that has been formed. And then we can say this, the difference in weight is what we actually called as the gravimetric analysis. So this is one of the easiest analytical method that we come across. Then now we'll, after gravimetry, we have another common technique, that is volumetry. Now volumetry, it relates to the measurement of the volume. So this method, it is based on the measurement of the volume of the reagent solution, which where we know the concentration of the solution, and this reaction is known as volumetric analysis. So here particularly the reagent, the concentration of the reagent and the volume that has been consumed during the reaction process is taken into account. So since it deals with the volume of the chemical reaction or the reagent, this analytical technique is called as volumetry. Now volumetric analysis, mostly we see this is done by titration, and hence this method is known as titrimetry. So whenever we come across the term volumetry, it directly means that we are talking about titrimetry. Now titrimetry, it involves the titration. So what is titration? So titration is basically we take a known amount of the reactant and then we take a burette. The titrant is added from the burette to the reactant till we reach the end point of the reaction, or what we call it as the equivalence point, and then we use an indicator. So then we see a difference in the volume, which we call it as initial burette reading or the final burette reading. And from considering the value volume, the difference in the volumes, we can say the volumetric, the nature of the reagent, and this process is called as volumetry or titrimetry. So, however, one of the disadvantages of titrimetry is that the reaction, it occurs very fast. So, what happens is the addition of titrant for a very fast reaction will be, we will not be able to catch it. So that is why this titrimetry is performed in certain cases, whereas in most of the cases, gravimetry is done. Now, then coming to the classification of analytical methods, which is based on electrical methods. Now, electrical methods is it is also one of the techniques such as we call them as electroanalytical techniques, which uses electricity. So here it can be used they use different electrical quantities such as the potential, the current, the quantity of current, and the dielectric constant. So taking these into account, different analytical methods have been developed and they have been named differently. Like, for example, we have potentiometry, amperometry, voltammetry, coulometry, conductometry, and high frequency methods. So these are the methods that have been, these are the analytical methods that have been classified according to their electrical method. So first we'll start with potentiometry. So potentiometry, it is an analytical method and it is based on the measurement of the potential difference that occurs across the electrochemical cell. So that is why, since in potentiometry we measure the difference of the potential difference, so that is why this process is called as potentiometry. Now the word potential, it comes from the half cell potential, or which we call it as the electrode potential. So that is why, since it is one form of electrical method that uses potential difference, and when we titration is formed by this method, we call it as potentiometric titration. So here in potentiometric titrations, we discuss the titration curves, that is the redox titration curves based of the either of the half cell reactions, and then we find out the nature or the oxidation state of our material, that is called as the analyte. The substance that we are analyzing is called as analyte. So here a special class of potentiometry where the potential of the pH indicator, where the potential of an indicated electrode is measured as a function of H plus ion, is called as pH metry. So in simple terms, when hydrogen ion concentration is taken, and then we call it as pH metry. So here this is what potentiometry is all about. Then the next is amperometry. Now, as the name implies, amperometer, it involves the measurement of current. So here the word amperometry is derived from the word ampere, which is the unit of current. So here in amperometric methods, here the what happens is we measure the difference in the current values, which gives us the we fix the current, and then with the difference is measured, which gives us the our required data. So here when the current is fixed at a the current at a fixed potential is measured as a function of titrant volume. So here in this case, on plotting data, two straight lines they are obtained. So whenever an amperometric titration, it involves two polarized microelectrodes, then that is called as your sorry, that is called as biamperometry titration. So here whenever amperometry, it actually indicates the current here is measured as a fixed potential. So the potential is fixed and the current is varied, and then the whole process is called as amperometry. Now coming to voltammetry. So here in voltammetry, an electroactive species is either oxidized or reduced. So what happens as a result, the resulting current, it is measured as a function of the applied potential. So what happens is the current versus potential curves, they are plot, and these are called as IE curves. This is potential versus current plots. So now the shape of these IE curves, they determine the nature of our analyte that is taken. So here in voltammetry, we study the relationship between current and electrode potential. Whenever we use a special type of microelectrode, that is the dropping mercury electrode, this technique is known as polarography. So, and this you will read in gradually in other units. This is just the beginning, so we are not discussing in details. Then the current potential curves, that is the IE curves, they are known as polarograms or polarographic waves. So here from these graphs we can find out the E half, that is called as the half wave potential. And then we can find out the the quantity of the analyte that has been used, or the quantity of the current, and this is the use of polarographic waves. Now coming to coulometry. Coulometry, it is an analytical method that is based on the quantity of electricity that is consumed. Now we know this word coulomb, it is the unit of quantity of current. So now measuring here in coulometry, the current that is used that to either oxidize or reduce the analyte, and then we can find out the amount of current that is consumed. And then this process is performed by generally two techniques: coulometry at constant potential, which is known as potentiostatic coulometry, and the coulometry which is performed at constant current, this is called as amperostatic coulometry. So here coulometry can be done in two ways: we can either fix the potential or we can fix the current. So depending on the nature of our sample, so the coulometry is performed. So here what happens, so these methods, they are actually called as coulometric titrations, and particularly amperostatic coulometry has found greater applications than potentiostatic coulometry. Then next is your conductometry and high frequency methods. The measurement of conductance, that is, which is the conductance is the reciprocal of resistance, and this is also used in chemical analysis. So the methods that are based on this conductance measurements, they are called as conductometry. So here conductometry is mostly performed in two ways. So one, an analysis can be performed directly from conductance measurements, whereas in another case, conductometry is applied to determine the equivalence point of titrations, and this process is called as conductometric titrations. So conductometric titrations, where the change in conductance is related to concentration changes of the ionic species, they are most frequently applied. So whenever we talk of conductometric method, the conductance measurements, they are made by using alternating current at relatively low frequencies, and this technique has been modified to use frequency of higher frequency in the range of megahertz, and these methods are called as high frequency methods. So whenever in conductometric titrations high frequency is used, that is in the range of like some several megahertz, they are called as high frequency methods, and these methods have been applied to measure the dielectric constant for various types of electrolytes. Okay, so this is how analytical techniques have been classified on the basis of electrical methods. Now coming to classification of different analytical techniques on the mode of optical methods. So here optical methods, as we know, this the spectroscopic, most of the spectroscopic methods, they are based on the emission, absorption, scattering, or the interaction of electromagnetic radiation with a sample. So coming to the optical methods of analysis, some of the important spectroscopic methods are emission spectroscopy, absorption spectroscopy, UV visible spectroscopy, IR spectroscopy, that is infrared spectroscopy, fluorometry or fluorophotometry, turbidimetry and nephelometry, and the last is Raman spectroscopy. So these are not classical methods, these are the recently developing novel technologies that have been used, or that have found prominence in the world of analytical chemistry to analyze different types of analytes. So the first we'll start with emission spectroscopy. So here, as the name implies, it is a method where the spectrum is produced by the excitation of elements to a certain wavelength. So whenever we talk of emission spectroscopy and absorption spectroscopy, it deals with the interaction of the matter with the UV visible range of the spectrum. So what happens here is, in emission spectroscopy, we see the nature of the excitation of the elements to a particular lambda, and then each element, they have a characteristic emission spectrum. So the emission spectrum for each material is different, and that is how we can quantitatively find out the from the spectra we can find out the number of atoms that have been excited or the number of atoms that are present inside the sample and that do not take part in excitation. So this gives us an idea about the emission nature of the or the excited nature of the molecules. So here in coming to absorption spectroscopy, this is based on the measurement of the absorption spectra of the interaction of the electromagnetic radiation with our sample. So here particularly absorption means that how a chemical species it absorbs the photons of a particular region. Then we can find out the number of the quanta of light that has been absorbed by the by the molecules of our analyte. And then when the selection of the narrow wavelength is made, we use various types of filters, and whenever a filter is used we call it as filter photometry. So this is when the measurements, particularly when we in an absorption spectroscopy, when a monochromatory is used, that is a monochromatic chromatic radiation is employed in presence of a monochromator. This technique is known as spectrophotometry or absorption spectrometry. Now, for this particularly, there are various types of spectroscopic methods that have been named according to their usage in the spectral region that have been used. So first, like we have ultraviolet and visible spectroscopy. This is called as UV visible spectroscopy. The here the it involves the absorption of UV and visible radiation, that is 100 from 200 to 900 nanometers by different types of molecules or ions, and this is known as UV visible spectroscopy. Here, the range of this spectroscopy, UV visible, it lies from 180 to 780 nanometers, and it particularly talks about the transitions, the electronic transition that occurs within our sample when it absorbs the light. So here, these methods by UV visible spectra is very much useful, and it is a critical tool for identification of different functional compounds and elucidation of the unknown structure. So however, but particularly although UV visible is used, however they are not confirmatory. This is just it gives us a preliminary idea about our sample. Then next coming to IR absorption spectroscopy. Now infrared spectroscopy, here the range is 0.78 micron to 1000 micron. So here in this case, when a molecule is subjected to IR region, the different types of functional groups that are present in the molecule, they show different types of vibration. So accordingly, looking at the wavelength at which the molecule absorb vibrates, we can say that nature of the functional groups that are present in the molecule. Now in general, IR spectroscopy, it has been divided into three classes, that is near IR, middle IR and far IR. Here it's IR, actually it is most of the IR that has been carried out, it is mostly in the middle IR region, and it finds particular mention in the case of organic compounds because it gives us an idea about the different functional groups, the identification of different functional groups in organic compounds. So that is the one of the most important uses of IR spectroscopy. Now coming to fluorophotometry. So here in this case, the energy of the photons of the incident radiation, it changes during the absorption to the excited state. So what happens here is when we take a photoluminescent substance, that is those are sensitive to light, after we excite them with light, they again give back their radiation. So this radiation, the re-emission of the radiation which occurs immediately is called as the fluorescence, and which occurs lately is called as the phosphorescence. So the measurement of this fluorescence or intensity of fluorescence is known as fluorophotometry or fluorimetry. Now, whenever we talk of phosphorescence, that is when the re-emission of the radiation it takes place much delayed, then the phenomenon is phosphorescence, and the technique that uses this phosphorescence is called as phosphorimetry. So this Here, both fluorimetry and phosphorimetry, they make use of the nature of the re-emission of the radiation by the that is absorbed by the molecules. Then next coming to turbidimetry and nephelometry. So these two methods, they are applied to determine the concentrations of suspensions, colloidal solutions, where small solid particles, they are homogeneously dispersed in our liquid medium. So the methods which here the analytical method where determinations are made by measuring the opacity of such solutions, that is known as turbidimetry. So here we measure the opacity with the help of the measurement of the transmitted light, that is called as turbidimetry. Now here the analytical method which is based upon the measurement of intensity of the scattered light by the colloidal particles, that is called as the nephelometry. So what happens here is in turbidimetry we measure the intensity of the transmitted light by the colloidal particles, whereas in nephelometry we measure the intensity of the scattered light by the colloidal particles. But the major drawback of these two processes are that they give very erratic results, and that is why they are not very accurate or precise, and they cannot be used for very small quantity of solutions. They are just preliminary, and a large volume of solutions are needed to know about the nature of the colloidal particles. So next is Raman spectroscopy. So here Raman spectroscopy is one important process which that involves the scattering of radiation in solution following Raman effect. Mostly when Raman effect, it means the scattering of light by a material, no, neither transmitted nor absorption. Raman always indicates scattering of light. So the shift in wavelength in Raman effect is caused due to extraction of energy from the quanta of the incident radiation. So we have a Raman shift that measures the difference in the absorption of the light versus the scattered light. So the difference in this, it gives us the Raman difference, that is called as delta nu bar. So Raman and infrared techniques, they are complementary to each other. So very important, an important advantage of Raman is that the Raman spectra can be collected over water, whereas IR spectra, it cannot be aqueous solutions, cannot be used for IR spectra. So in all effect, Raman spectroscopy is an advantage technique than IR spectra. Now then coming to classification of different analytical techniques based on nuclear methods. So some of these methods are radiochemical methods, radiometric methods, isotopic dilution methods, activation analysis, Mossberg spectroscopy, NMR, and mass spectroscopy. So these are some of the common methods that utilizes the nuclear methods. Now we'll talk about radiochemical analysis. So here very small amount of radioactive substances, either natural or artificial radioactive substances, they make the development of sensitive and analytical methods. They are here, they are used, called as radiochemical methods. They have been classified into three categories, namely radiometric analysis, isotopic dilution method, and activation analysis. So these methods, they have high sensitivity, specificity, and good accuracy. These methods, they have been discussed in later sections. Now coming to radiometric methods. So here particularly in radiometric methods, we take a radioactive reagent to separate the analyte completely from the bulk of the sample, and then the activity of the material that has been isolated is measured. So this is called as, sometimes this method is also called as radiometric titration. Then is isotopic dilution method. So in an isotopic dilution method, a known amount of the same substance with that contains an active radioisotope is added to the unknown sample. So after mixing both this, the quantity of the substance in the original material is then determined. So this technique is quite suitable, and the one of the advantages is that it does not require the separation, quantitative separation of the analyte. We just add another isotope to our original material. Then is activation analysis. The methods of activation analysis are based upon the measurement of radioactivity that is induced by the samples during irradiation with other particles such as neutrons, protons, deuterons, etc. However, thermal neutrons from a nuclear reactor, they are most commonly used, and this technique is therefore known as NAA, that is neutron activation analysis. Then coming to Mossberg spectroscopy, the analytical methods, that is here it is based on the study of the phenomena of resonance fluorescence of gamma rays, and that is why they are termed as Mossberg spectroscopy. Here it involves intranuclear energy levels, and here one of the important characteristic of this radiation is that we obtain extreme sharp lines. So that is why we will study this in later. Here Mossberg spectroscopy is also an advanced technique that finds quite uses in organic chemistry. Then coming to NMR. So NMR, it is based upon the measurement of absorption of the electromagnetic radiation by the nuclei of certain atoms or isotopes under the influence of a strong magnetic field. This is how NMR is important. Now we know that a nucleus has its own spin, and we have an external magnetic field. So as a result, the magnetic dipole, it is oriented and it is changed. So we see the position and signals of the NMR spectra then guide us to know the structure of our unknown organic compound. So here another method that is analogous to NMR is the electron spin resonance or ESR, which is based upon the absorption of microwave radiation by an unpaired electron when it is exposed to a magnetic field. So here when we in NMR we look at the position of the atomic nuclei when they are exposed to a magnetic field, but in ESR we look into the position of the unpaired electron that when it is exposed to microwave radiation in presence of a magnetic field. So these two processes, they are analogous to each other, NMR and ESR. And then coming to mass spectrometry. So here it is a method that is based on the study of converting molecules into charged particles like ions, their separation, and it is based on this on the mass to the charge ratio, and then we measurement of the relative intensity of the lines. So here mass spectrometry, it can provide both qualitative and quantitative information about the atomic or the molecular composition of the sample. Here it is very much important for an unknown organic compound we can know the types of compounds, their qualitative analysis and quantitative analysis from mass spectrometry. So this is also a very useful phenomenon. Then coming to classification of analytical techniques based on thermal methods. So here thermal methods are actually they are various types of thermal methods are there. So some of the commonly used thermal methods are TGA, that is thermogravimetric analysis, DTG, that is derivative of thermogravimetry, DTA, differential thermal analysis, DSC, differential scanning calorimetry, and TET, that is thermometric enthalpy titrations. So although the names here, from the names we can understand the types of the nature of the methods that have been used. So first we'll start with TGA. So TGA is thermogravimetric analysis. Here in this process we measure the amount of mass lost as a function of increase in temperature. So what happens here is, here the sample is heated from a lower temperature to a high temperature, and then the loss in the weight of the substance or our sample is measured. And that is why when we plot the graph, the plot is measured as here in the x-axis temperature is taken, and in the y-axis the mass loss is plotted. So that is why this is called as a thermogram. So the plot of a TGA, it is called as a thermogram, and here we can know the thermal stability of our sample from a TGA graph. Then is DTG. Here DTG means the derivative of the thermogram. So here when we have obtained the thermogram and we take the first order derivative, the plot of the first order derivative, it gives the DTG plot. So here in the DTG plot, it is prepared as the y-axis, it indicates the dW by dt, that is the change in the first derivative of the change in weight versus T, that is the temperature. So here in both this case, we do find in the DTG, we see a maxima and a minima. And particularly in case of TGA, when we conduct a TGA, the graph is not clear as it does not indicate the glass transition temperature or the melting temperature. So in order to avoid this, the first derivative plot, that is the DTG, it is plotted, and then we can clearly see the glass transition temperature and the melting temperature. So that is why these two processes are almost the same. Then coming to differential thermal analysis. So here the difference in temperature between the sample and reference, it is measured. So from the plot of delta T versus T, the transition temperature and the nature of the change, that is whether it is exothermic reaction or the endothermic reaction, it can be determined from a DTA analysis. Then coming to DSC. So DSC is differential scanning calorimetry. So here, as a function of temperature, we see the delta H, the change in delta H, that is enthalpy, with respect to temperature, it gives us the DSC plot. So it also talks about the thermal stability of the molecule. Then coming to thermometric enthalpy titrations, that is TET. The thermometric, here the titration process is followed by the measurement of enthalpy change during the course of the reaction. And for this, so during the course of the reaction, measurement of enthalpy change is a very difficult task, and that is why they are performed under controlled conditions in a small dewar flask, and they are, that is why they are called as thermometric enthalpy titrations. So these are some of the methods that uses the thermal analytical methods that uses the thermal nature, the thermal properties or the thermal modes of analysis for analytical techniques. Then coming to classification of separation methods. So we have seen, suppose we have an mixture of a compound, so therefore it is very necessary to analyze or for determination the classification or the separation of the unwanted materials from our substance. So here some of the processes for separation are the classical methods, which includes precipitation, distillation, sublimation, or by formation of complexes. But in modern methods, we use chromatography, solvent extraction, ion exchange, and electrophoresis. So these process, they will be discussed in your in MCH-002, in that is another unit, but today we'll just see about the gist of these methods. Now, chromatography, as we know, it is a very commonly used separation technique. So here the sample is applied on a stationary phase over which the mobile phase is located. So the various solutes that are present inside the sample, they are separated as they migrate based on their speed of migration. So chromatography, as we know, they are of different types. So based on the types of the materials used, we can say that is paper chromatography, TLC, liquid chromatography, HPLC, GC, partition chromatography, and others. So chromatography is one of the most common techniques that have been used for separation of organic, inorganic, and biochemical substances. Until date, it is also used, and novel processes are being developed. Technology has been developed using this chromatography techniques. Then is solvent extraction. So here in solvent extraction, a desired solute, it can be extracted by distributing it between two immiscible liquids. Here the principle is that two immiscible liquids must be taken, and then the solute is extracted from it. So however, solvent extraction can also be applied as a single stage procedure or as a multi-stage procedure depending upon the nature of our sample. Now another separation method is ion exchange. Here it is ion exchange. The principle is very simple. Here an insoluble material, which we generally term as an ion exchanger, it comes in contact with the electrolyte solution, so which we call it as the counter ions, and it releases the ions of the similar charge into the solutions. So when we take the cations as exchangeable ions, we call them as cation exchangers, And when we take anions, we call them as anion exchanges. So this is actually ion exchange is a reversible process. So the exchanged ions, they can be replaced by other ions of like charge. So particularly ion exchange has been used for the separation of rare earth elements, but like the F block elements, lanthanides and actinides, they have been mostly used for separation of these elements and sometimes in amino acids. Then the one other separation method is electrophoresis. So as the word electro implies, here the movement of charged particles occurs under the influence of an electric field. So what happens here is, if we have the different components of a mixture and we apply an electric field, then the particles present inside the mixture, based on their size, they move with different speed, thus and they are separated. This method has been used particularly in biological cases for separation of nucleic acids, amino acids, hemoglobins, and small organic and inorganic ions have also been separated with the help of this technique, and that we call it as ionophoresis. Both are the same things. Then coming to criteria for evaluating the utility of analytical technique. Why analytical techniques are important for us, particularly in science and in industries? Because to begin with, whenever we come across an unknown substance, now we know as technology is developing, so we do come across development of novel materials. Now when we have an unknown material with us, the first basic thing that we need to start is the percentage of the contents of its contents that is present inside the material. And this can be done with various techniques like mass spectrometry, NMR, HPLC, and IR, and then we can actually know the structure of the compound. This knowing the structure of a compound is important, because suppose in drug design we do not know the structure of the compound, then we cannot direct it to our use. So for now, for in drug development, the identification of the structure is much important. So here it is actually an interdisciplinary character to understand the cat structure of a particular compound. So here the results of a typical quantitative analysis, they are based on the two series of measurement. One is the gravimetry and the second talks about the amount of desired constituent. So here we can say, in order to understand the criteria, a complete analysis of the can actually be done of any material can be done using the following steps. First is the sampling, second is the dissolution of the sample, third is separation of the interfering substances, fourth is measurement, and fifth is interpretation. Now to begin with, sampling is very much important, because during this sampling process, each type of materials, they have their own sampling instructions, and that is why, so accordingly, the characteristics of the material, the quantity, its purpose, they are designed. Then second step is the dissolution. So most analysis have been are performed here. The choosing a particular solvent, a suitable solvent that dissolves our sample under conditions with no loss in our material is very much important. So firstly, in most cases, inorganic samples, they are first treated with dilute HCl followed by HNO3, or they are fused with acidic or basic flux. Now when we talk of organic solvents, organic solutes, they have been used for organic solvents. So that is why, so for the first, in order to know the nature of our sample, we need to understand its dissolution in any solvent. Then comes the separation of interfering substance. Now whenever a new material is prepared, there are substances that interfere or that prevent the direct measurement. Therefore, always separation of the interfering or the unwanted substance is necessary. So there is two ways to achieve this: either by isolating the desired constituent in the measurable form, or by removing the interfering substances. So in most of the cases, the substance of interest, it is transformed from one phase to another. So therefore, we have different separation procedures, so which such as like that involve the transfer of one phase of our substance to another, such as solid solid, liquid liquid, solid gas or liquid gas. So this is how we change the phase of our required substance into another. Then comes the actual measurement of our or the analysis of our substance. So here we can start with gravimetry, we can again start with volumetric. So here most of the first thing that we need to find the value of the empirically the value of the intensity factor, its concentration. So these are various, the success or failure of it is dependent on the proper selection of method. So analytical chemistry, it can save much time and improve the accuracy of the results by various factors. Although no simple rule, there are some of the, no simple rule has been prescribed, but some essential characteristics which must be considered are that the complexity of the materials, the concentration of the species, the accuracy, the sensitivity, the selectivity, the duration, or the cost of the equipment that is used. So then comes the interpretation of the measurement. So once we have performed the measurement, the interpretation of the data is much more important. So we should always remember that the results are reliable if they are strictly, if the conditions are strictly followed and strictly obeyed. So any deviations, it leads to error and loss in accuracy. So some, that is how a complete analysis of a material is done. Now emerging needs and recent trends, with the recent trends, analytical chemistry has been recognized to fulfill both the applied aspects of science and technology. So there are various, the earliest analytical determination was done by Lavoisier, who is considered as the father of analytical chemistry, and because of using the analytical balance. Then today, in terms of development of analytical chemistry, we have many novel technologies apart from classical methods which we still use today. We do come across various modern technologies and which are being developed with each passing day. We do come across development of novel instruments and how we can use instrumental methods, we can, how we can use and save our time, and that can help in faster recognition of the analyte. Thus there have been three major contributions in the vitality of analytical chemistry: the flow from theory into analytical chemistry, application of electronics by analytical chemists for assembling newer, faster, and more sensitive instruments, and application of both computers for data processing and automated control of instruments. So this has, the development of these three factors have led to a decrease in human time and labor, and we do hope that, and with the, in near future, other strong equipments with AI driven technology will be developed for analysis, which will make our analysis of the substance much easier and time saving. So here with this we complete this unit. So here we'll take a break of 5 minutes and then we will again resume with our second unit.
Madam, you are mute. Madam, you are not audible. You are. It is saying you are mute.
So now we'll start with Unit 2, that is evaluation of analytical data. So here in this unit, we'll talk about the different types of errors, the nature of the errors, and how we can report results on the chemical expression of the results, the numerical expression. What do you mean by significant figures, and how the evaluation of analytical data is performed. So here, so first we'll start with errors. Now, as we know, errors is the data that is always obtained whenever we perform an experiment or a physical measurement is done. Then it raises the question of errors and their nature. So now errors, various types of errors are there in quantitative chemical analysis. So therefore it is mandatory that we understand what an error is and the various types of error. So whenever we define an error, it is an inverse measure of the accuracy of a result. So here, the less is the error, more accurate the result is. Now, mathematically, we can write error, that is E is equal to O minus T, where E is the error, or we call it as the absolute error, and O is the observed value during the measurement, whereas T is the true value of the measurement. So here, with respect, here from equation 2.1, with respect to sign, we can also say about the nature of the error. Suppose we look into table 2.1. Here we consider a measuring flask whose capacity is 250 ml, and five measurements were done. So here five different measurements have been listed: 1, 2, 3, 4, 5. Then the observed value for this 250 ml, it was observed in one case as 249, 247, 250, 248, and 251. So now we know that the true value is 250, because we know from the beginning that we have taken a 250 ml flask. So for serial 1, we find out that the observed value was 249. So therefore, the error E here is minus 1. Similarly, in observation 2, we see that the observed value was 247. So therefore, the error is minus 3. So in observation number 5, we find that the observed value is 251, but we know the true value is 250 ml. So here, the error here is plus 1. So if we take the total of this error E, excuse me, we find the total is minus 5 ml and the average is minus 1 ml. So therefore, the error, it can be represented as the total error, that is minus 5, by the total number of observations, that is 5. So here it is minus 1 ml. So this is called as the absolute error. Here the absolute error is of practical little significance in a quantitative analysis, but When we talk of a relative error, that is relative, the error which is relative to the true nature, that is E by T. So here it is important. So to understand this, let us again understand what is relative error and what is here, what is an here. In this table we see three observations have been taken. We have taken three standard flasks, 10 ml, 100 ml, and 1000 ml. And the total true value here it is listed in the first row. The observed value it has been listed in the second row. Now, when we look into the error for A, B, and C, the error that is O minus T, in all the cases it has been 1 ml, 1 ml, and 1 ml. Now, but when we find out the relative error, so that is E by T or E upon T, in case A, it is 0.1, in case B, it is 0.01, and in case C, it is 0.001. And when we find out the percentage of relative error, that is into 100, we see this is 10%, this is 1%, and 0.1%. So now we can understand how the concept of relative error is of much importance than the concept of just error. So that is why whenever we report a data, it is reported in present in terms of percent RE. So therefore, we will again come across the different types of errors and how they are represented in analytical chemistry. So for practical point of view, an error has been classified into two categories. One that is called as determinate errors, and the second is called as indeterminate errors. So first we'll talk about determinate errors. Now here determinate errors are those whose magnitude can be determined after assigning a definite cause, and therefore they can be corrected. Like for example, when we take a hygroscopic salt, that is calcium chloride, that means it absorbs water. So if the weight of this calcium chloride, it will vary depending on the type of atmosphere it is exposed to. And thus the error caused by this absorption of water, if we keep this salt in a desiccator, then the error can be corrected. So the determinate errors, they may be constant or variable. When the determinate error possesses the same value from one measurement to another under a different set of conditions, it is called as constant error. Whereas in the other hand, the determinate errors that vary in magnitude, like the errors that may be caused due to expansion or contraction or volume, these where errors are called as variable determinate errors or systematic errors. So this is how they have been defined. Now coming to sources of determinate errors. Errors, they can be classified into three types, many types, but they have been mostly classified into five classes. So first is errors due to equipment, that we call it as equipmental error, like uncalibrated devices, uncalibrated measurements or weights or balances. So this arises due to the equipmental faults. Then errors due to reagents. The quality of the reagent is also very much important in qualitative analysis. So the error that is caused due to the incorrect standardization of the solution or the poor quality of use of reagent also leads to such type of errors. Then coming to personal error. So here in personal error, this occurs due to the errors of the person that is operating. Like for example, we see these are also called as psychological errors. Like due to some students, when they do some errors during the experiment, so these are actually labeled as personal errors. Then comes the operational errors. The operational errors, they are associated with the faults of the operation of the analysis, like they are independent of the instrument and therefore they are not related to the chemical properties. So they are mainly caused due to the carelessness of the operator. So that is why they are called as operational errors. Then comes methodic errors. So sometimes methodic, during the performing of an experiment, the, the methods that occur within the method and which cannot be prevented unless the whole method is changed, they are called as methodic errors. Now coming to indeterminate errors. Indeterminate errors are the errors where no exact cause is assigned, so they cannot be corrected. So they are most commonly called as random errors. Since no correction can be done for them, they are called as random errors. They can be prevented or eliminated by corrections. However, they can be considerably reduced by increased care in work. When we take extra precautions in our work, then such type of errors they can be eliminated. Now coming to detection and minimization of errors. So however, since we know that in case of indeterminate errors, no correction can be done. So other for determinate errors, we can perform some of the corrections. So the most important thing for analyst is to for the selection of the method of analysis. So here first is the calibration of equipment and purification of reagent. So the determinate errors that request is the calibration of the instrument. So rather here excuse me. So the calibration of the instrument is important, like calibration of the glasswares, use of purified reagents, use of proper samples, and that calls for the calibration of the instrument. Now, determinate errors, they are frequently caused due to the use of measuring devices that have been powered by electricity. Now, suppose we have a fluctuation in electricity, then these errors, they are detectable and they can be corrected. Then coming to use of blanks, the errors that are caused due to certain sources, reagents, vessels, and they can be used by what we call it as a blank sample or the control sample. Here the blank test is performed. So with the performance of the blank sample, we can deduct the unnecessary observations and then we can perform our own experiment. Then comes the addition of a standard. This method involves the addition of a known amount, that what we call it as a standard, and then it is analyzed. The measurement of sample plus standard is compared with the that of the sample alone, and then we can find out the our actual value. So this has been used in isotopic dilution method, radiometric analysis, and any other techniques. This technique has the great advantage that the standard and unknown, they are measured under identical conditions. So here this method is quite useful. Then we have independent analysis. Then detection of methodic errors is very difficult. So what we do is, these may be here the determinate errors, it can be detected by the analysis of a synthetic sample whose overall composition is known and it resembles to that of our own analyte. So here in certain instances, the determinate error of the method may be minimized by carrying out the analysis by a method of high accuracy, like gravimetric determination of aluminium. Here it involves the precipitation of aluminium as hydrous aluminium oxide and ignition to higher temperatures. So here in this method, how we can find out independent analysis of our analyte. Then improvement in methods. Now we can make our own improvements to modify the existing method for the better analysis of our samples. Then coming to accuracy and precision. Now we know accuracy and precision are vital to analyze our own data. So coming to accuracy, it is defined as the nearness of a measurement to its true value, or we call it as the accepted value. It is expressed in terms of error. So we know that less is the error, the more is the accuracy. Thus, after knowing the relative error, we can find out the loss in accuracy. Now, there are various ways to find out the accuracy of an experiment. Now, let us consider example 2.1. Now, here a sample was analyzed that having 2.62 gram as the true value. Then the results of three independent experiments were found to be 2.50, 2.254, and 2.52 grams. Now it has been asked to find out the mean error. So for measurement 1, we know the true value is 2.62, whereas the measurement value is 2.50. So the error is found to be minus 0.12. Similarly, we can find out the error for the other two cases, and then we can find out the total error. So as a result, we can find out the mean of this measurement by the total number of observations, that is 3. We can also find out the mean error, that is the total error divided by the number of observations, that is 3. And using this, we can find out the percentage relative error, that is given as by mean error by true value into 100, and the relative accuracy can be given as the percentage is given as mean by true value into 100. So this comes to be this. If the error is minus 3.8, we can directly subtract it from 100. So it gives us as 96.2. So this is how less is the error, more accurate is the experiment, and that is how we can find out the percentage RE, that is the relative error, and the accuracy. Now coming to another term, that is precision. We talked about accuracy, now we talk about precision. So here in precision, it is defined as the reproducibility of an experiment. It tells us about an agreement between the numerical values of different of the replicate experiment. So precision, it is a commonly it is expressed in terms of deviation. So less is the deviation, the result is more precise. The deviation, it is defined as the difference between the measured value and the mean value of the series of measurements. The deviation mathematically, it is given as xi minus xr x bar, where d is the deviation, xi is the number of observations, and x bar is the mean series of the measurements, that is given as sigma xi by n. So here deviation is generally taken without regard to any sign. So average deviation is given by the formula sigma xi minus x bar by n, and percentage deviation is given as percentage average deviation is given as average deviation by x bar into 100. So these are some of the formula that we need to remember, and the one of the most important formula is the standard deviation. So standard deviation is given by this formula, and then we find out the variation using the standard deviation formula. Variation is given by equation 2.4. These are some of the two important formulas that need to be remembered during calculation of deviation and variance. Now we need to understand the distinction between accuracy and precision. So here when we look at figure 2.1, it is a shooting profile by three person A, B and C. When we look into the profile of A, here all the dots, they have been concentrated at the center and they are all close to each other. So this indicates that the figure A is both accurate and precise. When we look into figure B, our target is actually in the center, but here we do not find any hits in the center. Rather, the hits have been at the outside, but the hits are all concentrated at one place. So this figure, it indicates that it is precise, but it is not accurate. However, when we look it into C, all the hits are at different places and they are not at the center, or they are concentrated at one place. They are all scattered randomly. That is why figure C, it includes that it is neither precise nor accurate. So this is how we designate accurate and precision. Accuracy and precision. So here the one of the most favorable methods that give us the those which give us precise at the and the time accuracy, we find out that is more in actually we need results that are more precise and accurate. So here we'll consider another example. This here in example 2.2, the burette readings of titrations carried out by three students has been shown. Here the true readings has been found to be 22.22, and the burette readings has been shown for ABC, and the mean value have been written. Now we will compare the accuracy and precision of A, B, C. So when we look into the values, mean value of A, we see that the mean value to 22.22 is the same as the true value of 22.22. So this is both precise and accurate for A. Now, when we look into B, the mean value was found to be 22.28, and here the true value is 22.22 ml. So here the mean value is on the higher side of the true value. So therefore the results of student B, they are precise but it is not accurate. Now when we look into the C for this, that is 22.18, it means that here it is neither it is close to the true value, or even if we look into this, the observations, they are not close to all the values. So this results is neither precise or it is neither accurate. So this is how we we segregate accuracy and precision. Then coming to reporting of results. So an analytical report, it is resulted in two parts. One is chemical method and another is numerical method. So chemical expression of results. So as far as possible, the result of the element, it should be reported in chemical form. So like for example, in the determination of inorganic ions, we write it in the terms of Fe3 plus, Ca2 plus or Cl minus. However, when the actual form is not known or other specific purpose, then this expression is modified. So when limestone is used for the purpose of manufacture of lime, calcium content, here it is expressed as calcium oxide. However, when we talk of the hardness of water, we usually express in terms of calcium carbonate. Although other ions are present in calcium, but we express it in terms of Ca2 plus. So this is how a chemical expression of data is done. Then coming to numerical expression of results. So here in most of the analysis, numerical expression is done. It represents the amount of the constituent that is present in the sample. Suppose we take W1 is the amount of our sample and W2 is the WS is the original amount of sample and C is the factor that is required. So here we have this expression. So thus we need to say that the using this formula or using any mathematical formula to find out the amount of our material of interest gives us the numerical expression of our analysis. Now particularly for solids, how we do a numerical expression for particular analysis. For solids, we do it in the terms of weight of the constituent into 100 parts of weight of the sample, or we write it in terms of parts of the analyte in 100 parts of the sample. So whenever we consider liquid analytes, they have been expressed in three ways. Like one in terms of weight percentage. So weight percentage is given as weight of our constituent of our particular constituent into 100 by weight of the sample. Similarly, we have also have weight volume percentage, that is weight of the constituent into 100 by volume of the sample. Also we have volume percentage that gives us the volume of our constituent by volume of our sample into 100. So these are the three ways in which liquid samples, the numerical expression for liquid samples, they have been done. Then we, for particularly for gaseous sample, they are done in terms of percentage volume, that is volume of the constituent by volume of the sample into 100 at a particular temperature. When we talk of gases, the temperature should be specified. Also for other measurements, we have ppm, or that is parts per million, or we have ppb, that is parts per billion, or ppt, parts per trillion. So there are various ways of representation of our numerical expression of analytical data. Then coming to significant figures. So significant figures, they are we know they are very much useful, particularly when we talk of a number. It implies a mathematical expression. Here number is any of the characters from 1 to 9. So the digits of a number which are needed to express the precision of the measurement from which the number was derived, they are known as significant figures. Like the digit from 1 to 9, they are always part of significant figures, while 0 may not be a significant figures. So suppose if we take the number of 542, the figures that signify here are 500s, 4 tens, and 2 units, and therefore they are all significant to each other. Now, 0 it has been used in two ways. It may be used as a significant figure, or it might just indicate a decimal place. Now, when 0 is a part of the measurement, then it is significant. Like if we say the weight of the crucible is 12.610 gram, here the terminal 0, that the weight can be measured up to third place of decimal. The 0 after 1 is significant because this is the part of the measurement. Similarly, for this 0.100, the three zeros after the 1, they are all significant in nature. Now, suppose we consider this 107.2. The 0 between 1 and 7, it is significant because 0 is placed between two significant numbers, that is 1 and 7. This number has four significant figures like 1072, 10.72, 1.072, and 0.000172. So, that is how we understand the significance of 0. Now, suppose to write a result with some degree of certainty, the correct use of significance must be made, which depends on various rules for computation. So first is observed quantities. They should be recorded with one certain figure retained. That is, there must always be significant figures in a result. Thus, in when most of the cases, we represent the significant figure by plus minus 1. So supposing we write 22.6 ml as 22.6 plus minus 1, this means that it is found to be significant between 22.5 and 22.7. Okay, so in rounding of quantities, to desired number of significant figures by dropping the superfluous gap figures, for example, here we see 46.2368 rounded off to four significant figures, it becomes 46.24. Now, if the dropped digit is exactly 5, then the last figure would be rounded to the nearest even digit, that is 3.55. Rounded off to two significant figures is 3.6, whereas 3.65 rounded off to two significant figures is also 3.6. 14.75 rounded to one decimal place is 14.8, and 2.652, that is rounded to one decimal place, is 2.7. So this is the general mathematics that we all know of. Now, when 226.4332 rounded to four significant figures is 26.43. This we are also aware of. This is how rounding off nose is done. This is pure general mathematics. Now, in addition or subtraction, the answer is rounded off to the significant figures in terms of the least significant unit. It is mainly for decimal places, and the numbers having the fewest decimal is the least significant unit. Now, supposing we see 26.234 is rounded off to 26.23. Here this is 3.223 is rounded to 3.22. 143.4 here it is retained, and 2.2260 is rounded off to 2.23. The sum of these factors is 175.08. Now, if we round it to one decimal place, then 175.08 becomes 175.1. So this is how in addition or subtraction rounding off is done. Now, coming to multiplication and division. Suppose after calculation, for example, we look into this multiplication. 7.0783 into 0.00305 into 6.602. The middle factor has got the least significant figures, and hence we can write it as 7.078 into 0.00305 into 6.602. So this becomes 0.145142523. So, and when we round it off to three significant figures, it becomes 0.143. So this is how in multiplication we round off the significant figures. Now, if a calculation it involves addition, subtraction, multiplication and division, then we have to perform the rounding off separately. Now, when a calculator or computer is used, all available digits must be included, and then the final result will be rounded off. One extra figure may be included in average. So in logarithm calculations, as we understand a logarithm, it consists of two parts: the characteristic part, which is a whole number, and the mantissa, that is the decimal part, and hence it is the same regardless of the position of the decimal. For example, to express properly the logarithm of 2.4 into 10.4, the characteristic is 4 and the mantissa is 0.3802, which is the logarithm, and the logarithm is 4.3082. This result is rounded to 4.38 since the given number, that is 2.4, it consists of only two significant figures. Here in the example, it is given that calculate the pH of 4.0 into 10 to the power minus 3 molar HCl, solution of HCl. So if we look into this, the pH is minus log H plus, and here the minus 3 into 10 to the power minus 3, the pH becomes minus of minus 3 plus this, and 3 minus this, so we get 2.40. This is how significance is done. So here in summary, we can say that errors have been classified into two types. One is determinate and another is indeterminate. The determinate errors can be corrected, whereas indeterminate errors, they cannot be changed. That there are two terms, that is accuracy and precision, that is frequently used in analytical data. The accuracy tells to the nearness of the true value, and the precision, it talks about the reproducibility of replicate transmissions. The smaller the determinate error, then the more accurate is the result. A result may be precise even without being accurate. On the other hand, a result cannot be accurate unless it is precise. The correct use of significant figures, which is dependent on the application of various computational rules, is of fundamental importance. So thus, in reporting the results, so the important computational rules for correct use of significant figures has also been discussed. So these are some of the questions that are associated with this unit that needs to be done. And here some of the terminal questions relating to the errors and the finding of the significant figures, they have been done and the answers have been provided. So it is advised that you should perform this, you should go this, and with this we complete the first part of the analysis of the analytical data, and then we'll start with unit 3. So here unit 3, it talks about, as you can see, it talks about the evaluation of analytical data part 2, that is in terms of, we just came across standard deviation, and here in this unit 3 we talks of the average deviation, probable deviation, the mean data, the confidence level, and various such factors that are important for the analysis of analytical data. So here in this unit 3, we will just have some important terms, begin with some important terms. Like first, we call it as the mean. Now we know mean. What does the mean of any data means? It means that it is the sample mean, which is represented as x bar, and it is the arithmetic average of all the observations, that is given as sigma xi by n. This we all know. And for an entire population of the data, the mean population is represented by mu, and it is given as capital mu is equal to sigma xi by n, where tends to infinity, and it is the number of capital N. It implies the number of observations, a very high number of observations that approaches the unity. So here we also have another term that we call it as the median. Now median is, it is means the middle value. Suppose we have a set of observations, the mean value, the middle value, it implies the median. It is used, median is a advantageously, it is used when a set of analytical data, it contains a probable result. So among this, the middle value, among all the possible results, the middle value will imply the median. Then we have a common term that is called as mode. So mode means the observation which occurs maximum, that is most of the times. It is called as mode. It is another quick measure of central value. So like for in the given set, if we look into this, 12.6 is the mode because among all the data it occurs 4 times. That is why it occurs the maximum time and it is called as the mode. Now coming to deviation. So here deviation means the error which it cannot be that cannot be stated if the true value of the quantity is not known. It is meaningful to take the difference between a particular measured value and the arithmetical value, and this difference is called as deviation for apparent error. So here mathematically we can write it as capital D is equal to mod of x minus mu. So this is how it is called as deviation. Then we have the average deviation or AD, and this is given as sigma of di by n. That is where the symbols have the usual meanings. With relative to average deviation, we have a concept that is RAD, relative average deviation, which gives AD by x bar into 100. So hence, when we multiply average deviation into 100, we get it by we express, we call it as RAD, relative average deviation. Then we have probable deviation. Probable deviation, it means it is defined as the deviation having a magnitude that there are equal numbers of deviation between greater than and smaller than itself. This is also called as probable error. Then comes range. The difference between the largest and smallest value, it is known as the range. It tells about the spread of the data. The range of the data is known from the highest and the smallest observation in a particular set. Then coming to standard deviation. Standard deviation is the very important statistic to understand the precision of a analysis. So here from equation 3.6 we can know this sigma. This is called as population standard deviation. It is given by this formula from equation 3.6. Sample standard deviation equation 3.7, and using all this we can calculate the standard deviation of a given data, that has been illustrated in example 3.1. Then coming to standard deviation of the mean. The standard deviation of the mean is given by d by root over of n. We also have standard deviation of the mean given by equation 3.10, and it is called as standard error. The formula of the variance in terms of sample and population has also been given here. If all equation has been done, so you can go through the solved examples and find out. Then coming to relative standard deviation and coefficient of variation. So here RSD, or we call it as the relative standard deviation, is expressed by SR S by X. So here percentage, in particularly when we express the percentage RSD, it is known as coefficient of variation CB. That is CB is equal to X by X bar into 100. So here student activity question has been given and you can find out the CB and percentage RSD. So with this, we have just touched some of the concept of deviation, standard deviation and deviation. So in tomorrow's class, we'll talk about the remaining about the precision of the computed results and the some of the errors and deviations in this part. Okay. So with this class is over for today, and we'll again start tomorrow at the precise timing, that is 6 p.m. So thank you for today.
Thank you, ma'am.
Thank you, ma'am.